Hello everyone, this is the team consisting of Arshdeep and Shreyas presenting the linear algebra project for the course EE5120. So the problem statement for our project revolves around the use of Markov chains and transition matrices to model the growth in economic distribution across different sections of the economy over time. So before we delve into the modeling part of it, we'll briefly gloss over the concepts of linear algebra involved in this. First and foremost, Markov chains. So a Markov chain or a Markov process is a stochastic model describing a sequence of possible events in which the probability of each event depends only on the state attained in the previous event and not the states preceding it. Another important concept related to Markov matrices is the transition matrix. So a transition matrix represents the dynamics of change between two states. So a transition matrix is used to model the evolution of one state into another state over time in a Markov process. So the properties of a Markov of a transition matrix is that the sum of the columns of a transition matrix is always 1 and the entries of a transition matrix always lie between 0 and 1 since they are transition probabilities. Now coming to our linear model for growth analysis. The economic distribution at any given time is represented using a stochastic state vector, as in each value of an n-dimensional stochastic state vector represents the proportion of people living in that particular section of the economy, and the sum of all the values is always equal to 1. The transition matrix is used to model the dynamics of evolution over time. Hence, our growth equation becomes T into Pn minus 1 is equal to Pn, where Pn minus 1 and Pn are the economic distributions at n minus 1 and nth time step, and T is our transition matrix. Now coming to the steady state analysis using transition matrix. So here we'll go over and show that what the steady state for a transition matrix means and how we can calculate that using eigenvalues. So for a vector S is called the steady state of a transition matrix T if T into S is equal to S, which basically means irrespective of the number of times we multiply the transition matrix to this vector, the vector state does not change. Another way of looking at this is that S is an eigenvector of the transition matrix with an eigenvalue corresponding to 1. So if you want to find the steady state of a particular transition matrix, then all we need to do is find the eigenvector corresponding to the eigenvalue of 1. In the next step, we'll prove that for any given transition matrix, arbitrary transition matrix, there will always exist an eigenvector corresponding to the eigenvalue of 1, implying there will always be a steady state for any given transition matrix. Now going over the proof, we know how that to find the eigenvalues and the eigenvectors, we write the characteristic equation given by the determinant of T minus lambda I is equal to 0, where I is the identity matrix. Now since we're interested in the eigenvector corresponding to the eigenvalue of 1, we substitute lambda is equal to 1 and get determinant of T minus I is equal to 0. Now as mentioned previously, we know that the sum of the columns, each column in a transition matrix is equal to 1, and we are effectively subtracting 1 from each column of the transition matrix. Thus the sum of each of the columns of the matrix T minus I will be equal to 1 minus 1, that is 0, which implies that T minus I is not a full rank matrix and its columns and rows are linearly dependent. Hence the determinant of T minus I will always be equal to 0, thus implying that an eigenvector corresponding to the eigenvalue 1 will always exist. Hence a steady state is always achievable for any given transition matrix. Now that we've glossed over the linear algebra concepts, we'll come to the modeling part. So to define a stochastic state vector, we divided the countries of the world into 3 parts based on their GDP per capita as compared to USA. If the GDP per capita as compared to USA was greater than 0.4, then they were in the high bracket, and if it was between 0.1 and 0.4, they were put in the middle bracket, and if it was less than 0.1, they were put in the low bracket. Empirical data was used to determine the stochastic state vectors for the 1980 and 2000 period. Similarly, studying the growth of individual countries over this time period, the transition matrix for this time period was defined. So as evident, this is the stochastic state vector for 1980, this is the stochastic state vector for 2000, and this is the transition matrix. Now, as mentioned previously, we do the eigenvalue decomposition of this transition matrix to obtain the steady state. This vector is not normalized, and since the sum of the columns of stochastic state vector need to be equal to 1, we normalize this vector to finally get the steady state. So using our analysis, this we get the following results. Using empirical data in 1980, 0.28% of the total countries were in the high bracket, and by our study we predict that 0.34% of the total countries will be in the high bracket once the steady state is achieved, and similarly 0.33% of the total number of countries were in the low bracket in 1980, and this number will increase to 0.38 once the steady state is achieved. This result is particularly disturbing, was particularly disturbing for the economists of that time, because it showed that the world economy will diverge into twin peaks, as in there will always exist an income disparity between the very rich and the very poor countries, which is not sustainable for the world. Now we've performed some preliminary analysis to show these results, and I'll take us to the collaboratory Jupyter notebook. So as we showed in the analysis, we've defined that transition matrix and the 1980 state vector, and if we multiply the 1980 state vector with the transition matrix, we get the state vector for 2000, and if we keep on repeating the process, we can calculate the state vectors for 2020, 2040, and so on. So first what we'll do is, using the eigenvalue analysis, we'll compute the steady state. So we've done the eigenvalue decomposition of the transition matrix and calculated the steady state as mentioned here. Now what we'll do is, we'll recursively multiply, as mentioned here, the transition matrix to the initial state vector and calculate and see the evolution of the economic distribution over time. And once we plot the results, we see that the economy indeed is twin peaked, as the proportion of countries in the low bracket saturate to 0.38 and the proportion of countries in the high bracket saturate to 0.32, whereas very few countries remain in the middle economy bracket. And in the end, if we multiply the transition matrix for a very large n, let's say 20, and compare the results with the steady state obtained, we see that the results are pretty similar, showing that the eigenvalue decomposition method for computing the steady state indeed works. Next, we come to show that why the previous model is flawed, and how we can make corrections to the previous model to show that the world economy will not diverge into twin peaks, but instead converge to a single peak. So the two fundamental flawed assumptions in the previous model was that it assumed the world population will remain constant and no interaction/migration will occur between the different sections of the economy, which is not a realistic assumption. And the third and the most fundamental flaw was that the transition matrix was assumed to be constant over different periods of time, but in our further analysis will show that the transition matrix is not stationary, and indeed it is a dynamic matrix that evolves, and which means it is different for different time periods. So coming to the construction, so another study was conducted in the year 2000, where it was shown that if we use the transition matrix of the 1970 to 1990 period and apply the same matrix in 1990 to do the predictions for 2010, the values obtained is drastically different from the empirical data, which goes on to further prove that the transition matrix is not steady, and there was a different transition matrix for the 1990 to 2010 period than the 1970 to 1990 period. So for this study, for further precision, the economies of the world was divided into 6 different stages using empirical data, and using this empirical data between 1970, 1990 and 2010, 2 transition matrices were calculated, one respectively for the period of 70 to 90 and another one for the period of 1990 to 2010. And as evident, the transition matrix for the 70 to 90 period was different from the transition matrix for the 90 to 2010 period, hence proving that M is dynamic and not a stable matrix. So to overcome this difficulty, we come up with a method of modeling this dynamics. So we introduce another matrix Z called the evolution matrix. So the concept of evolution matrix is that if we multiply Z with Mi, that is the transition matrix for a given time step, then we get the transition matrix mi plus 1. That is mi plus 1 is equal to z times mi. So the z matrix is used to model the evolution of the transition matrix. So in our new model, to obtain the pkth steady state vector, we do not multiply t power k minus 1 into p1 to get pk. Instead, we multiply pi I is equal to 1 to n minus 1 mi into p1 to get pk. So, in coming to the conclusion part of it, if we use the evolution matrix method to predict the world economy in 2050, the results are very optimistic, as it shows that a large number of countries, that is 44, will be in the high economy bracket, and only 11 countries will be in the low or tier 6 bracket, as compared to the non-evolution matrix based method, which predicted that only 5 countries will be in the tier 1 bracket and 34 countries will be in the tier 6 bracket. So the evolution based model has been able to match the results obtained empirically for 2010, and it further goes on to show that the world economy will converge to a single peak in the near future, which is a very optimistic result to look for in the future. That is all from our side. Thank you.